Okay, now we get to the part that I'm sure you've all been waiting for, math. This entire video is going to be working out 3 different kinds of equilibrium problems. First one is right here. A mixture of hydrogen and nitrogen in a reaction vessel is allowed to attain equilibrium at 472 degrees Celsius. The equilibrium mixture of gases was analyzed and found to contain 7.38 atmospheres H2, 2.46 atmospheres N2, and 0.166 atmospheres NH3. From these data, calculate the equilibrium constant Kp for the reaction. N2 gas plus 3H2 gas is in equilibrium with 2 NH3 gas. Okay, this one is a straightforward, ordinary, everyday plug and chug. Kp, we know, equals the pressure of NH3 squared over the pressure of N2 times the pressure of H2 cubed. But we know all those things. Pressure NH3 is 0.166 squared over 2.46 times 7.38, and that one's cubed. Little handy dandy plug and chug. And we get 2.79 times 10 to the negative 5th. Done! Okay, now here's the next problem. It's a little harder, so pay close attention. A closed system initially containing 1.000 times 10 to the negative 3rd molar H2 and 2.000 times 10 to the negative 3rd molar I2 at 448 degrees Celsius is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of HI is 1.87 times 10 to the negative 3rd molar. Calculate Kc at 448 degrees Celsius for the reaction taking place, which is H2 plus I2 goes to 2HI. Okay, now the thing to notice here is there's 2 different sets of conditions that they're talking about. Initially, you have in the beaker 1 times 10 to the negative 3rd molar H2 and 2 times 10 to the negative 3rd molar I2. But you have no HI. All you've put in the beaker is the 2 reactants. Then you let this reaction react until you've reached equilibrium. At that point, you have 1.87 times 10 to the negative 3rd molar HI. And we don't know how much H2 or I2 we have. Now, in order to try to analyze this equation, or this problem, we are going to introduce a technique that we are going to use for the next 3 chapters. This is called an icebox. I-C-E. This is going to let us organize the information that we have been given. I stands for initial, C stands for change, E stands for equilibrium. Okay, so initially we had 1 times 10 to the negative 3rd molar of H2, and we had 2 times 10 to the negative 3rd molar I2. I'm not going to write all those zeros. You realize they're in there for sig fig purposes. Okay, and I have none of this. That's what I've got initially. At equilibrium, I have 1.87 times 10 to the minus 3rd molar of HI. Okay, so let's think about the change. What changed here? I formed this. Where did this 1.87 times 10 negative 3rd come from? Why, it came from H2 and I2, right? I added here, this is the change, I added 1.87 times 10 to the minus third. How much of this did I take away? Oh look, stoichiometry rearing its ugly head. There's a 2 there, a 1 there, and a 1 there. So if 1.87 times 10 to the negative third moles, or molar, HI was formed, half of that must have left I2 and H2 because of the 1 to 2 ratio. You can convince yourself with that with a little stoichiometry. 1.87 times 10 to the minus third moles per liter. For every 2 moles of HI, there's 1 mole of I2 or H2, whichever one you want. 1.87 times 10 to the negative third divided by 2 is 0.935 times 10 to the minus third. Well, I've just written it that way so we're all in the same exponent. Okay, so that means this guy was plus 1.87 times 10 to the negative third. This guy is 0.935 times 10 to the minus third negative. Now you see why there were 3 zeros there. And this is also negative 0.935 times 10 to the minus third. So whereas I had 1 times 10 to the minus third, I have now lost 0.935 times 10 to the minus third because it got used up making this. Okay? So 1 minus 0.935 gives me 0.065 times 10 to the minus third. And also here. Now this one's 2 times 10 to the minus third minus 0.935 times 10 to the minus third, so that's 1.065 times 10 to the minus third. Oh look what I've got. I've got equilibrium values. Ha! Now that's a plug and chug, just like it was in the previous problem. I know. The K is the concentration of HI at equilibrium squared over the concentration of H2 times the concentration of I2, which is 1.87 times 10 to the minus third squared over 0.065 times 10 to the minus third times 1.065 times 10 to the minus third. Once again, I take out my handy dandy calculator, I plug and I chug, and the answer actually comes out to be 51. And we're done. If you want to study that problem and how it works some more, it's actually in your book. It's sample exercise 15.9 on page 645. Okay, that one was kind of hard, huh? This one's even harder. Okay. A. 1 liter flask is filled with 1 mole H2 and 2 moles I2. Nice, they gave us a 1 liter flask, so these moles are the same as molarity. Okay, so we don't have to worry about that. Well, we know now the value of the equilibrium constant Kc, it's 50.5. What they want to know now is what are the equilibrium concentrations of H2, I2, and HI. Okay, so this is essentially backwards of the problem from before, because before we were plugging in equilibrium values and finding K. Now we're plugging in K and finding equilibrium values. Okay, so the first thing we need is an ice box. H2 I2, 2HI, ICE. Okay, what do we know? We know initially we have 1 molar of H2 and we have 2 molar I2. And we have no HI. All they did was they put H2 and I2 in the beaker and waited for it to reach equilibrium. But they didn't tell us, like they did before, the equilibrium value of the product. Now this time we'll have to think about that a little more. Okay, so the first thing we know about this reaction is the first thing that's going to happen is the forward reaction. There can't be any reverse reaction at the beginning because there isn't any product. So we know we're heading from reactants to product. Okay. We also know, once again, the stoichiometry of the equation. So while we don't know how much HI is going to get formed, we're going to call that X, how much HI is changing, it's getting formed. We do know it's going to be twice the amount of I2 and H2 that are getting lost. Notice that's all coming from the stoichiometry of the equation. So whatever it is that's getting formed, there's twice as much of it as we're losing here and here. Okay? So now once again, just like I did before, I'm going to combine I and C to get E. So this is 1 minus X, this is 2 minus X, and this is 2X. Alright. Now K, we know is 50.5. We also know it's the concentration of HI squared over H2 times I2. And we only know those values in terms of X, so we are going to plug those right in here. 50.5 equals 2X, the quantity squared, over 1 minus X times 2 minus X. Whew! Man, what a big pain that is. But it is solvable. It's just ugly algebra. So, pause the video right now and rearrange this guy into a quadratic equation. Okay, I have assumed you have rearranged this, and that's what it comes out to be. 46.5 x squared minus 151.5x plus 101 equals 0. Now you have to do the quadratic equation. I assume you all remember how to do the quadratic equation. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Plug, chug, and out comes the answers. H2 is 0.065, I2 is 1.065, HI is 1.870. If you would like to see that all worked out for you, it is in the book. It's sample exercise 15.12, which is on pages 648 and 649. But try to work out the math yourself first before you go and look this up.